One of the things I find that is always vague about quantum mechanics is perhaps the most important question. What makes a system a quantum system? That is, what is the fundamental property shared by all systems that are described by quantum mechanics? We're going to go through some of the usual answers and see how they don't work, and then we'll discuss what I personally think is the defining property. And we will see how that property by itself is enough to recover, at least qualitatively, many of the surprising quantum behaviors. So let's get started. One thing some people say is that quantum mechanics is about fundamental objects. This describes electrons, photons, the smallest, most fundamental constituents. And it is true that to describe those systems we must use quantum mechanics, but it is not true that only those systems are quantum systems. In some circumstances, in fact, we model a complex system, one we know that has a substructure, as a single quantum object. So a proton, an atom, and even a molecule behave in some cases as a single quantum object. For example, they interfere and diffract. And even for fairly sophisticated ones, like a barric ball, we use the same equations. Moreover, we should also note that protons were once thought to be fundamental particles. Only once they were probed at high enough energies, their inner structure was revealed. So for all we know, electrons may not be fundamental at all. We just haven't reached high enough energies. So given that we use quantum mechanics for objects that are not fundamental, and given that strictly speaking, we can't even know for sure whether an object is truly fundamental, the idea that quantum mechanics applies only to fundamental objects does not work. So let's try again. Some say that it is about size. This is what I was told. Quantum mechanics is for small objects and classical mechanics is for big objects. But again, this fails. We know we can make large objects that obey quantum rules. We can take two entangled photons, separate them by 1,000 kilometers, and they're still entangled. They form a single quantum system. So size does not seem to matter. Some say it is about size, but not size as in volume in space, size in number of constituents. So simple objects, one with a few particles, are quantum, while complex objects, ones with many particles, are classical. And again, this does not work. Large objects can exhibit quantum properties. Superconductivity and superfluidity are quantum effects, and this can be achieved with macroscopic systems, which have a large number of particles. So this does not work either. So it's not fundamentality, it's not physical extent, it's not number of constituents. What is it that makes a quantum system quantum? And my answer is irreducibility. A quantum system is irreducible, meaning that in the context in which it is being studied, the description of the whole cannot be reduced to the description of the parts. The processes which the system is subjected to are not sensitive to its internal dynamics, to what happens inside, which remains hidden. Is the atom or proton interacted at high enough energy that the internal structure matters? Well, if not, then we can treat them as a single quantum system. Otherwise, the state is in terms of the constituents. The atoms or proton is not a single system. The idea of irreducibility allows us to understand what is different between classical and quantum mechanics. Classical systems are reducible. Describing the whole is equal to describing the parts, while quantum systems are irreducible. Describing the wholes tells us nothing about describing the parts. So let's see what I mean with a couple of examples. Suppose you have a ball, we can throw it and study its motion. Or we can take a red marker and make a red dot on the ball. And we can study the motion of the red dot. Now, studying the ball is equivalent to studying all possible red dots that we could put on the ball. So the state of the wholes tells you everything about the state of the parts and vice versa. And we say the ball is reducible. The idea is that assuming infinitesimal reducibility, that we can make arbitrarily small red dots, recovers classical mechanics. Phase space, position, and momentum represent the state of infinitesimal part, the particles, and a finite object is a distribution over phase space. Many people don't realize this, but classical phase space is exactly the structure that we need to make the density coordinate invariant, relativistics, so that we are assigning densities to states no matter what units or reference frames we use. We can assign densities to infinitesimal parts, so classical systems are infinitesimally reducible. On the other hand, consider our electron. We can study its motion, but we can't take a red marker and keep track of what a part is doing. We can say we want to scatter a photon only on this part and not the rest. We can't study parts because we can't even define parts. We can only study the whole electron. Therefore, in this case, the state of the whole cannot tell us anything about the state of the parts. Even if the electron is made of finite mass, we can't say which part of that finite mass is doing what. If it is scatters with a photon, we can't say what part of the energy of the photon was absorbed, reflected, re-emitted, and so on. So the electron is irreducible. The idea is that irreducibility is enough to recover quantum mechanics. We can't have a full distribution of positional momentum. We can't know what the parts are doing. So we have a distribution over position alone, or momentum alone. But even then, we can't track the motion of individual parts of the distribution. We can only say what the whole distribution is doing. The state of the electron then is automatically an ensemble because it does not specify everything. And there is an intrinsic uncertainty that comes from the undetermination of its internal dynamics. And it turns out that complex numbers happen to be the right tool to capture how the variance of this undetermination combines. We'll see more in detail some of these ideas in other videos, but what's important here is that quantum mechanics can be fully understood, or at least I think so, in terms of irreducibility. So what we're going to see now is how irreducibility by itself can explain, at least conceptually, many of the quantum effects. At the beginning we saw how composite systems like proton, atoms, and molecules can behave like a single quantum system. They can diffract and interfere. So when can they do that? When can we treat them as a single quantum system? The idea is that we can treat them as a single quantum system precisely when the process that acts on the system is not sensitive to the internal dynamics, to what the constituents are doing. In that case, the system can be assumed to be irreducible. So, for example, at low energy, a proton will behave like a single particle. But at higher energy, we're going to start interfering with the internal dynamics. We will be interacting with the quarks directly, so at high energy, the proton is not irreducible anymore. It cannot be modeled as a single quantum system. Next, entanglement. What does it mean for two systems to be entangled? Well, it means that they form a single quantum system that they cannot be understood as just the sum of its parts. The system is not reducible to independent parts. You can't describe one photon without describing the other photon as well. But if you start interacting with only one side so that the process is sensitive to only the dynamics of one part, that's where you break the entanglement. If you measure the speed on one photon, then the process is sensitive to the state of only one part, so you break the entanglement. You now have two independent systems. The wave-like nature. Because the internal dynamics is not accessible, it is not determined. The state has to be an ensemble over all possible internal dynamics. The quantum states therefore describe a distribution in terms of the parts. Note that we can't say exactly whether the distribution describes parts that are actually spread out, as in an actual wave, or just jiggling around, as in a probability distribution. To do so, we would need a process that is sensitive to the internal dynamics of the part, but we can't by assumption. We assume that the system is irreducible. So we are stuck. We are sort of a hybrid in between, and that is why you have these weird features of quantum mechanics. The particle-like nature. As the system is irreducible, we interact with the whole or nothing. We cannot absorb half a photon or interact with half an electron. So the system is a unit, and in this sense, the system is a single particle, as long as the assumption is valid. Quantum uncertainty. The uncertainty, which is really underdetermination, comes from the inability to describe the parts. If we were able to prepare position and momentum perfectly, it would mean that all parts would also be prepared at the same position with exactly the same fraction of momentum. No movement, no uncertainty. But that means we'd know exactly the state of all parts, which is forbidden by assumption. So there must be a lower limit to that precision. Non-locality. From the uncertainty, we saw that the quantum system must be distributed in space, but it has to behave as a single unit. We can't interact with one part of the system in a region without affecting the whole, even if the rest of the system is somewhere else. If we could interact only with part of the system within a region, we would violate irreducibility. We would be able to interact with a part. Since we always interact with the whole, that interaction then must be non-local. But the non-local interaction has to be such that we cannot learn anything about the parts. So we can't use it, for example, to transmit a signal, as that would require we could describe the internal dynamic of the system. Interference. When parts that are spread spatially overlap, there would be correlation as their dynamic are not independent. If the parts were independent, we could study the internal dynamics. So we will have constructive interference if the dynamics is correlated, and destructive interference if the dynamics is anticorrelated. So the superposition is just a linear combination of the stochastic description of the undetermined internal dynamics. Naturally, one could go through each effect and say a bit more. But the point here is that all these effects can be seen as a consequence of a single property, irreducibility. We can study the whole, but the internal dynamics is not accessible. The processes at our disposal are not sensitive. So what makes a system a quantum system? What makes a system a classical system? It's whether the state of the whole tells us anything about the state of the parts. In classical mechanics, it tells us everything. In quantum mechanics, it tells us nothing. Both of these are assumptions, a realization, that we can take in some situations. It doesn't matter whether they're strictly true or false. In fact, no system is truly infinitesimally reducible. And we can't really rule out that at sufficient high energy, we will find subtraction within an electron. So you should really think about the reducibility and irreducibility as working assumptions. We take them because they're useful to make the problem simple. What is important is that they help us guide our intuition when applying the theory, and that in some circumstances we can take them as sufficiently good approximations. And again, be aware that this is how I look at things. It is the view of our project, Assumptions of Physics, but I find that helps me understand things more. And we'll see in other videos that it plays well with the math as well. So that's why I hold this view, because it's useful. And it's certainly no less reasonable than a bunch of other things people say about quantum mechanics.